Hello viewers, in today's session we are going to discuss one important definite integral, right? So here in this class we are going to evaluate the value of this definite integral in which we are going to use some important properties of definite integrals and some standard result from indefinite integrals, right? So here we have to evaluate this integral from 0 to pi, and the integrand is x divided by 1 plus cosine square x. So let us take this integral as I, right? So we know that an important property of definite integral which says that if we have an integral from 0 to a f of x dx, then this integral is equivalent to 0 to a f a minus x dx, right? So what we do in this integral, we replace this x by a minus x, right? So here we have 0 to pi, so the value of a is pi, and the function f of x is given by x over 1 plus cos square x. So let us apply this property to this integral, and let us call this integral as integral number 1. And applying this property, we can now write 0 to pi, and here we replace x by a minus x. So it means we have to replace x by pi minus x in the second step. So we have pi minus x, and here we have 1 plus cos square pi minus x, and this is dx. And now using some trigonometry, we know that cos of pi minus theta is given by minus cosine theta. So this is a standard result from trigonometry. So here we have 0 to pi minus x, and here we have 1 plus cos pi minus x is minus cos x, and which is minus cos x square, right? So now we can write this integral as 0 to pi minus x, and here we have 1 plus minus 1 square is positive, so we have simply cos square x, and here we have dx, right? So let us split this integral at this point, that is the negative sign pi minus x. So let us write it as 0 to pi. The first integral is pi dx over 1 plus cos square x. The second integral is negative. Here we have the negative sign, so this is 0 to pi. Here we have x dx over 1 plus cos square x, right? And now if we closely look at this integral, this is our original integral I, right? So now we can write it as 0 to pi. Here we have this integral. Let us take pi outside the integral because pi is a constant. So we have pi dx. Here we have 1 plus cos square x, and this integral may be replaced by I, right? And now taking this I to this side, we have I plus I, and this is pi 0 to pi and dx over 1 plus cos square x. I plus I is now equal to 2i, and taking this 2 to the denominator of pi, we now have I is equal to pi over 2 and 0 to pi, and here we have dx over 1 plus cos square x. So let us call this integral as integral number 2. So now let us convert this cos square x into secant square x. So we know that secant x is equal to 1 over cos x. It means cos x is equal to 1 over secant x, right? So I can be written as pi over 2. Here we have 0 to pi, and we can now write dx over 1 plus 1 over secant square x. For cos x, we can write 1 over secant x, and simplifying this term, we have pi by 2. This is 0 to pi, and here we have secant square x times 1 is secant square x. Here we have 1, and taking secant square x to the numerator, we have here secant square x, and here we have dx, right? Now here we can apply one important trigonometric identity, that is 1 plus tan square x is equal to secant square x, right? So let us write this secant square x as 1 plus tan square x, right? So we'll replace only this secant square x by 1 plus tan square x, and the secant square x in the numerator, it remains as such. So we have I, this is pi by 2, 0 to pi. We have secant square x dx, and here we have 1 plus tan square x plus 1, and here we have dx. So this is pi by 2, 0 to pi. This is secant square x dx, and here we have 1 plus 1 is 2. So we have tan square x plus 2, right? Now we'll solve this integral by making use of the concept of substitution method. So now, before applying the substitution method to this integral, we'll make use of another important property of definite integral, which says that if we have the integral from 0 to 2a f of x dx, then this integral is given by 2 times 0 to a f of x dx, right? Provided f of 2a minus x should be equal to f of x. So this property is also an important property of definite integrals, which says that if we have 0 to 2a, so the upper limit is 2 times a, and here we have the function f of x, then this integral is equal to 2 times the integral from 0 to a, right? So now the upper limit becomes only a, that is half of 2a, and we have f of x dx. So this expression is valid only when this condition prevails, right? That is f of 2a minus x should be equal to f of x. So let us apply this property to this integral. Now see, here we have pi, right? So we can now write this integral as pi by 2, and we can write 0 to 2 times pi by 2, because there is no harm in writing pi as 2 times pi by 2, because 2 and 2 are going to be cancelled, right? So we can write pi as 2 pi over 2. So now our a, this a is equal to pi by 2, and here we have 2, and f of x is secant square x over tan square x plus 2, and here we have dx, right? So now we have to see whether this condition is applied or it is valid for this function. So here f of x is secant square x over tan square x plus 2. So f of 2a minus x. So 2a, a is pi by 2. So we have f 2 times pi by 2 minus x, which is again f of pi minus x, right? So f of pi minus x is given by secant square. Here we have, for x we can write pi minus x. Then we have here tan square pi minus x plus 2, right? So now we know that secant pi minus x is given by negative of secant x, and similarly tan of pi minus x is given by negative of tan x. So secant square pi minus x is square of this term, that is negative secant x squares, and it becomes a positive. So we have simply secant square x, and similarly tan pi minus x is negative tan x, and when we make the square, then this negative sign becomes positive, so we are left with tan square x, and here we have 2. So this function is again equal to this one, which is our original function f of x, right? So we can see that this condition holds for this function, that is secant square x over tan square x plus 2, right? So now we have pi by 2, 0 to 2 times pi by 2 secant square x over tan square x plus 2 dx. So now we can write this integral as here we have pi by 2. So now we have 2 times, because here we have 2 times 0 to a. So we have 0 to a, which is pi by 2. So we have here secant square x over tan square x plus 2, and here we have dx. So now this is our integral I. Here 2 and 2 get cancelled. So we have I is equal to pi times 0 to pi by 2. Here we have secant square x over tan square x plus 2 dx. Now let us make the substitution here, and we can take u is equal to tan x, right? So we can differentiate u with respect to x. So du over dx is secant square x. So we have du is equal to secant square x dx, right? So here we have secant square x dx, and let us change the limits accordingly. So here x varies from 0 to pi by 2. So when x is 0, then u is tan 0. Tan 0 is 0. And when x is pi by 2, we have u is equal to tan pi by 2. And this is not defined. So we can write it as infinity, right? So now we have I is equal to pi, and we have 0 to infinity. Here secant square x tan x can be written as that is du, and in the denominator we have u square plus 2, right? So this is pi. Here we have 0 to infinity du, and this is u square plus 2 can be written as the square of square root of 2, right? Okay, so now we have a very standard integral, and we know from indefinite integrals, that is dx over x square plus a square is given by 1 over a and tan inverse x over a, right? So we are going to use this result to this integral. So we have pi. Here we have the variable u. Here we have x, and this is a square. A square is our square of root 2. So a is square root of 2. So we have 1 over a, 1 over square root of 2. Then we have tan inverse x over, that is u over square root of 2. And we have the limits from 0 to infinity. So now let us substitute the limits, and we'll take the difference. So we have I, and we can take square root of 2 outside. Here we have pi over root 2, and we have simply tan inverse u over square root of 2, 0 to infinity, right? So we have pi over square root of 2. And when we take u is equal to infinity, we have simply here tan inverse of infinity and then minus tan inverse of 0 over square root of 2, which is simply 0, right? So first we take u is equal to infinity, then u is equal to 0. So we have tan inverse infinity minus tan inverse 0. So here we have now pi over square root of 2. Tan inverse infinity is pi over 2 and tan inverse 0 is 0, right? Because we know that tan pi by 2 is infinity and we have pi by 2 is equal to tan inverse infinity, right? And similar is the case with tan inverse 0. So now we have pi over square root of 2 times pi over 2. So we have pi square over 2 times square root of 2, right? So here's the value of this integral is equal to pi square over 2 times square root of 2. So this is how by making use of the concept of the properties of definite integrals and other results from trigonometric functions, we can evaluate this integral. So the value of this integral is given by pi square over 2 times square root of 2. So 2 times square root of 2 is 2 root 2. Hello viewers, in today's session we are going to discuss a very important definite integral in which the integrand is of the form 1 over square root of q, where q is a quadratic polynomial, that is ax square plus bx plus c, right? So here we have the integrand of the form 1 over square root of q. So now here we see that we have the integral from 0 to 3, and here we have 1 over square root of 3x minus x square dx. So let us call this integral as I, and here the quadratic polynomial is given by 3x minus x square, right? Okay, so now to solve these type of integrals, what we usually do, we try to make a perfect square, that is we'll try to express this quadratic polynomial in terms of a perfect square, right? So for this what we will do, we'll first take because here the coefficient of x square is minus 1. So what we will do, first step is to take negative sign common from these two terms. So we have x square minus 3x, right? Okay, so now we have minus, and now we'll write this term as x square minus 3x over 2. Here we'll write a 2 in front of 3x, and then we'll add and subtract the square of 3 by 2, right? So here we'll write 3 by 2 square, then we'll subtract 3 by 2 square, right? So this is the usual method of changing a quadratic polynomial into a perfect square. So now we have x square as a square, then we have the term 2ab, right? So here we have 3 by 2 whole square as b square, right? And the middle term, that is 2 times 3x over 2 is minus 2ab, right? So a is x and b is 3 by 2. So now these three terms give us the square of a minus b, right? And here we have minus 3 by 2 square, that is 9 by 4, right? So we have expressed this quadratic polynomial q as minus, here we have a minus b whole square. So this is x minus 3 by 2 square, and then we have here minus 9 by 4, right? Because if we again expand this square, we'll get the same term as 3x minus x square, right? Because see, here we have a minus b square, so we have a square, then we have b square, that is plus 9 over 4, then minus 2ab, that is 2 times, here we can write x times 3 by 2, and here we have minus 9 by 4. So 9 by 4, 9 by 4 get cancelled, and here 2 and 2 also get cancelled, so we have minus x square, and this is simply 3x, and now we can write it as 3x minus x square, right? So we'll get the same quadratic polynomial. So now we can write our integral I as 0 to 3, then we have dx, and here we have square root of minus uh, x minus 3 by 2 square minus 9 by 4, which can also be written as 9 by 4 minus x minus 3 by 2 square, right? So multiplying these two terms by negative sign, we have now this quadratic polynomial. So we can write it as 9 by 4 minus x minus 3 by 2 square. So now to move further, what we will do, will make use of the method of substitution. So let us take a new variable z, that is equal to x minus 3 by 2. So dz over dx, differentiating z with respect to x, we have dz over dx is equal to 1, because the derivative of x with respect to x is 1, and derivative of 3 by 2 being a constant, it is 0, right? So we have dz is equal to dx. Now the limits of integration vary from 0 to 3. So when x is 0, then the value of z is 0 minus 3 by 2, that is minus 3 by 2. And when x is 3, then the value of z is 3 minus 3 by 2, that is 6 minus 3 over 2, that is 3 over 2, right? So now the integral I can be written as the limits are from minus 3 by 2 to 3 by 2. For dx, we can write dz, and in the denominator we have square root of 9 by 4, which can be written as 3 by 2 square, and here we have z square. So now to integrate this function, will make use of a standard result. So we know that the integral dx over a square minus x square is given by sine inverse x over a. So this is a standard result here. So we have a as 3 by 2, and the variable x is z here, right? So now the integral dz over square root of 3 by 2 square minus z square is given by sine inverse x over a. X is z and a is 3 by 2, right? And the limits are from minus 3 by 2 to 3 by 2. So I can be written as sine inverse 2z over 3, and limits are from minus 3 by 2 to 3 by 2. Now substituting the limits, and we'll take the difference. So here we have sine inverse 2 by 3 times 3 by 2. The upper limit is 3 by 2, then minus, here we have sine inverse 2 by 3 times minus 3 by 2, right? So 2 and 2 get cancelled, 3 get cancelled, so we have sine inverse of 1, and here we have sine inverse of minus 1, because 3 and 3 get cancelled, 2 and 2 get cancelled, and we are left with only a minus 1. So we have sine inverse 1 minus sine inverse minus 1, and this is sine inverse 1 plus sine inverse 1, because we know that sine inverse minus theta is equal to minus sine inverse theta. So this negative can be taken out, and here minus and minus becomes plus. So we have now 2 times sine inverse 1. So now the value of this integral I is given by 2 times sine inverse 1 plus sine inverse 1 is 2 sine inverse 1, and sine inverse 1 is pi over 2, and 2 and 2 get cancelled, and we are left with only pi, right? Because sine pi by 2 is given by 1, so that sine inverse 1 is equal to pi by 2, right? So the value of this integral is given by pi. Hello viewers, in today's session we are going to discuss a very conceptual and important problem from definite integrals, right? So here in this class we are going to evaluate this integral that is from 0 to 2, and here we have 4 minus x square raised to 3 by 2. So let us start. So here we are going to use the method of substitution, and let us call this integral as I, right? So we'll substitute here x square is equal to 4 times t, where t is our new variable. Now x can be written as square root of 4 times t, and x is equal to 2 times square root of t. So basically we are going to substitute x is equal to 2 times square root of t, and t is our new variable. So let us differentiate x with respect to t. So dx over dt is equal to 2 times the derivative of square root of t, right? And the derivative of square root of t with respect to t is 1 over 2 times square root of t. 2 and 2 get cancelled, and we have 1 over square root of t. So now a dx can be written as dt over square root of t, and let us change the limits accordingly. So here x varies from 0 to 2. So when x is 0, then the value of t can be obtained from this relation, right? So t is x square over 4. So when x is 0, we have 0 square over 4, that is 0. And when x is 2, which is the upper limit, so t is 2 square over 4, that is 4 over 4, that is 1, right? So now let us transform this integral I in terms of t. So now we have I is equal to, the limits vary from 0 to 1, and here we have 4 minus x square is 4 times t, and here we have 3 by 2, the power is 3 by 2, and dx is dt over square root of t. Now let us simplify this integrand. So we have 0 to 1. We can take 4 common from these two terms. So we have 4 raised to 3 by 2, 1 minus t raised to 3 by 2, and here we have dt over t raised to half, right? So now we can write I is equal to 4 raised to 3 by 2 is given by 4 cube raised to half. So this is 64 raised to half, that is 8 square raised to half. 2 and 2 get cancelled, so we are left with 8. So here we can write 8, and taking 8 outside the integral, we have 0 to 1, and we can take t raised to half to the numerator. So we have t raised to minus half, and here we have 1 minus t raised to 3 by 2 dt, right? Okay, now let us rewrite this integral as 0 to 1. T raised to minus half can be written as t raised to half minus 1, and here we have 1 minus t raised to 5 by 2 minus 1, and here we have dt, right? So now we have converted this integral into the beta function. So now from the definition of beta function, we know that beta m comma n is given by 0 to 1, and here we have t raised to m minus 1, 1 minus t raised to n minus 1 dt. So this is the famous Euler's integral, which is also known as the beta function, and here m and n are greater than 0, right? So we can now write this integral as 8 times, here we have beta of half comma 5 by 2. So the value of m is given by half, and the value of n is given by 5 by 2, right? So now we have this integral I as 8 times beta half comma 5 by 2, right? Now we can convert this beta function in terms of gamma function, and we know that beta m comma n is given by gamma m times gamma n divided by gamma of m plus n, right? So this integral I is now 8 times gamma of half, here we have gamma of 5 by 2, because m is half and n is the 5 over 2, and here we have gamma of half plus 5 by 2, right? Okay, now we know that gamma of half is given by square root of pi, and gamma 5 by 2 can be written as 3 by 2 plus 1, and which can be written as 3 by 2 times gamma of 3 by 2, and here we have 3 by 2. Gamma 3 by 2 can be written as half plus 1, so this is 3 by 2 times half, and here we have gamma of half, right? So this is 3 by 2 times half times square root of pi, because gamma half is square root of pi. So here to get the value of gamma of 5 by 2 as 3 by 2 times half times square root of pi, we have used here the result, that is gamma n plus 1 can be written as n times gamma of n, right? So now our integral I takes the form, we have 8 times gamma of half is the square root of pi, and gamma of 5 by 2 is 3 by 2 times half times square root of pi, and in the denominator we have gamma of half plus 5 by 2, which is 1 plus 5 over 2. This is gamma of 6 over 2. This is gamma of 3, and we know that gamma n plus 1 is given by n factorial, where n is some positive integer, right? So here gamma 3 can be written as gamma of 2 plus 1, which is equal to 2 factorial, that is equal to 2 times 1, that is 2, right? So here we have 2. So now we have 8 times square root of pi times square root of pi is pi. Here we have 3 over 4, and here we have 2, so we can write it as 1 over 2. So 4 times 2 is 8, so here 8 and 8 get cancelled, and we are left with only 3 times of pi, right? So viewers, the value of this integral is given by 3 times pi. So this is how, by making use of the concept of beta gamma functions, we can evaluate these kind of integrals.